Hi everyone, I'm Yuechuan from the University of Utah, and today I'm going to give a talk on wireless hydrogel-based glucose sensor for future implantable applications. My talk will be outlined as the following. I will start with a brief introduction, and then I will talk about our proposed hydrogel-based wireless implantable glucose sensor. In particular, I will talk about the synthesis of glucose-sensitive hydrogel and inductive sensing principle characterization, low power data transmission, wireless powering, and prototype wireless sensor module packaging. After that, I will present our measurement results and end this talk with conclusions. So here are some examples of commonly used glucose sensors, such as finger prick glucometer, urine dipstick, subcutaneous sensors, and contact lens-based glucose sensors. So there are actually various limitations associated with these sensors. First is point measurement of blood or urine sample that leads to non-continuous monitoring capability. And some measure interstitial fluid or tear that suffer from a delayed response from blood glucose change. And more importantly, these are all enzymatic-based methods, so they are prone to long-term performance drift. Therefore, these are inadequate for future long-term implantable continuous monitoring applications. So why implantable glucose sensors? Nearly 30 million Americans suffer from diabetes and about 400 million worldwide. Diabetes has become a global pandemic and can cause severe life-threatening complications, such as cardiovascular disease, stroke, eye problems, nerve damage, kidney failure, birth defects, amputations, to name a few. So an implantable glucose sensor that provides continuous and direct monitoring of blood glucose level will be a critical sensing element for a future closed-loop insulin delivery system, for example, artificial pancreas. So the authors has identified several critical requirements for future implantable glucose sensors. First is the miniaturized sensor module, for example, a few cubic millimeter size, with wireless capability for sensor data telemetry, wireless powering, or recharging. In addition, a sufficient implant depth is required to access blood, which pose a severe challenge for small sensor wireless connection. And also, a robust biocompatible package is critical for long-term continuous monitoring, and of course, accurate measurement and fast response and long-term stability is also equally critical. So with these requirements in mind, we have proposed the following glucose sensing architecture. And as you can see here, the sensor is implanted in a blood vessel with the wireless powering from outside skin and wirelessly transmitting the glucose signal from the inside. So here we use a functionalized hydrogel embedding a metallic sensing plate as our sensing element. The hydrogel can change its volume in response to glucose, therefore causing a displacement of the embedded metallic sensing plate and further cause a inductance change of the coil inductor down below. And this inductance change can be sensed wirelessly through a frequency modulation scheme. We also propose to use a reference hydrogel which is not glucose sensitive to serve as a reference to suppress environmental effects. So there are actually two key advantages associated with this sensing architecture. First is we use hydrogel sensing that overcomes the limitations associated with enzymatic glucose sensors. Hydrogel itself is just a polymer device, and polymer materials. And the second is the sensing electronics can be encapsulated in a hermetically sealed package, for example, a glass package or silicon package. And the way we can do that, the reason we can do that is because this sensing scheme does not require a direct contact between the electronics and the hydrogel or sensing plate. So this is our electrical system design architecture. As you can see, there are wireless RF powering at the front end, followed by an AC to DC conversion. And here we use a voltage regulator to stabilize the DC voltage and power a sensing oscillator that transmitting the glucose information and the reference oscillator suppressing the environmental drifts. So next, I will talk about the glucose-sensitive hydrogel. So first, we form a pre-gel mixture using 4 monomers. And then, we modify the surface of a 10 micron Perylene C-coated metallic sensing plate. And next, we put this metallic sensing plate into a PDMS mold and pour the pre-gel mixture into the mold and cover the mold with a 400 micron thick gel bond film. And next, we expose the sample under UV light to initialize the polymerization. And then we take out the sample and store it in 1x PBS solution prior to testing. So important design aspect is during the whole process, we do not need any glue to secure the position of the sensing plate or the hydrogel. And this is due to the surface modification process shown here. So after surface modification, there is something called vinyl group on the surface of the metallic sensing plate, which is a double bond and will naturally combine with the hydrogel during the polymerization process. And the reason this is critical is for long-term reliability, because assume if you use glue to secure the position of any of these parts, then during the glucose cycle, the hydrogel will shrink and expand, and over cycles and cycles, you will see some delamination and limits the longevity of the sample. So for the prototype design, our size is kind of on the bigger side. It's a 3 millimeter by 3 millimeter XY dimension and 400 micron thickness. Because we are utilizing this vertical movement of the hydrogel, and this movement is directly proportional to the thickness. Therefore, the thicker the thickness, the more signal we will get. But we started with 400 micron as a starting point to explore the issues of the hydrogel test. And for the hydrogel we have fabricated, it shrinks with the increased glucose concentration. So for more information about the hydrogel, you can find it in this reference paper. So next I will talk about inductive sensing principle and characterization. So in the prototype design, we have this 3 millimeter diameter coil inductor placed 100 micron away from a metallic sensing plate. So this coil will induce an eddy current inside of the metallic sensing plate that creates a counteracting magnetic field. So what this counteracting magnetic field does is it will cancel out part of the original field from the coil and reduce the coil inductance. And because this field effect is a function of gap size, so when we modulate the gap size, we will see a change in inductance. And it is very critical to have a small initial gap size for high sensitivity. And here is the experimental setup where I changed the gap size using a mechanical actuator. And as you can see, when I plot the inductance value versus the gap size, when the gap size increases, the sensitivity actually drops. And this is due to the exponential decay in the near field. So we really want to operate in this lower gap size region to maximize the sensitivity. And here shows a sensitivity plot tested in air under that 100 micron initial gap size. So as you can see, we achieved the sensitivity of 4 nanohenry per 10 micron with a baseline inductance around 400 micron. So that corresponds to about 1% inductance change tested in air. And then we protected the coil using 10 micron parylene C and put it in saline solution. We also find that similar sensitivity. So here is the 3D finite element simulation of the sensing setup, where I have a spiral inductor and a sensing metallic plate down below. And as you can see, the eddy current is concentrated directly below the coil windings. So what this allows us to do is we can hollow out the center part of the plate without sacrificing too much sensitivity. And we can benefit from this is the increased diffuse rate of the glucose into the hydrogel, because now the top has an opening. But for the prototype design, we use a solid plate for simplicity. So this is the sensing coil inductor RF characterization. And as you can see, when we drop it into saline solution, the quality factor drops due to the conductivity of the surroundings. And we achieved the maximum Q frequency of 40 and a maximum Q of 20. So this is where we designed our oscillator to be around, so to maximize the Q quality factor of the oscillator. And we use the low power tunnel-diode oscillator as a data transmitter. So from this plot, as you can see, in the IV characteristic of the tunnel-diode, you can see there is a negative slope region that gives us a negative resistance. And when biased at 200 millivolt, we achieved a negative resistance about 1.2 kilo ohm, which is enough to compensate the tank loss of the L&C. And the change of the oscillator frequency can be approximated by this equation. So if there is a change in the inductance, there will be a change in the frequency, and it can be detected wirelessly from a nearby receiver. So the power consumption here is only 40 microwatts. And part of the reason we can achieve this ultra low power is because the supply voltage is very low. It's only 200 millivolts. So now this is the initial glucose test under DC power supply. In other words, this is not a fully wireless system yet. So in here, I placed my tunnel-diode oscillator PCB inside of a 9.5 millimeter 3D printed package and powered by a stable DC power supply. And this is the oscillator PCB, and this is my sensing coil. So it's very critical to push this sensing coil all the way down to the bottom of the package to minimize the overall gap size for higher sensitivity. And I will show you how I did that later on. And then I filled the package with PDMS to seal the electronics, and followed by a 10 micron Parylene C coating as a biocompatible, as well as a moisture-resistant layer. And then I adhere this previously synthesized hydrogel sample onto this 3D printed adjustable platform and assemble these two parts using screws. And next, I make adjustment of these screws so that the gap size between the top of the metallic sensing plate and the bottom of this package is about 50 micron. So 50 micron is a very small gap size. And you may wonder, how do I know it's 50 micron, not 60, not 70, not even 100? You cannot eyeball it, for sure. But what I did was I have a calibration test where I have a mechanical actuator to control the gap size, and I will record the frequency correspondingly. So when I make the assembly, by looking at the frequency, I can back out the gap size. And the sensor bottom plate has a finite thickness of about 80 micron. So the overall gap size is about 130. And once again, the small gap size is for higher sensitivity. And you probably have a question, so how is this package implantable? So we designed this package to prove the concept. For the future version, we will eliminate all these screws assemblies and tune the process to make the gap size right. And so in that case, everything will be one piece. And next, we immerse the sensor module into 1x PBS solution with a controlled glucose test. And it's very critical to cover the top to minimize or eliminate the water vaporization that can potentially change the glucose concentration. And a spectrum analyzer here is used as a receiver, and the receiving antenna is placed about 4 centimeters away from the sensor package. So this is a typical received RF power spectrum from that receiver. And as you can see, our oscillation frequency is 38 megahertz, which is close to that 40 megahertz we targeted. And the receiver position is 4 centimeters away. So what's going to happen when I change the glucose concentration is that when I increase the concentration, there will be a shrink of the hydrogel that makes the initial gap size larger and increases the inductance. And the increased inductance will correspond to a decreased frequency. So the frequency tone will actually move down to the left-hand side. So this is the glucose response under the DC power condition. And from this point to this point, I changed the concentration from 0 millimole to 10 millimole at a step of 2 millimole every 24 hours. And we observed a 20 kilohertz per millimole sensitivity for concentration below 2 millimole. And a reduced sensitivity was observed at higher concentration, which is about 8.5 kilohertz per millimole. So this reduced sensitivity is likely due to the saturation of the hydrogel at higher concentrations. And what's more important in this plot is actually this part. So when I don't have any glucose change, you can see there is a frequency drift, and here is, I show 5 kilohertz per day frequency drift, even though glucose is changing. So this drift is limiting our sensing accuracy, and I will talk about why we have this drift and how to eliminate it. So with this drift, we achieved a 0.2 millimole at lower concentration and 0.6 millimole at higher concentration sensing accuracy, in other words, resolution. So this DC power test is still not fully wireless, but it enables us to understand the behavior of hydrogel, the response time, and the packaging scheme. And next, we replaced that 200 millivolt DC power supply by this RF powering circuitry, where I have this RF power source to drive an external coil that inductively couple the energy into this internal RF power receiving coil, and the dimensions are shown here. So here we achieved a coupling distance about 2 centimeters. And this is what we consider deep enough for accessing blood. And here we use a Schottky diode as a half-bridge rectifier to produce 1.2 volt DC to bias this voltage regulator and further outputs a 200 millivolts to bias the oscillator. So the reason we use half-bridge instead of full bridge is because we want to minimize the voltage drop across the rectifier circuit. And you may also have a question. Since you already have 1.2 DC here, why bother using a voltage regulator to step down the voltage? Why don't you just make this voltage 200 millivolts and directly power the oscillator? The question is, you can do that, but although the oscillator frequency is primarily determined by the L and C, it's also a function of your bias voltage, because this tunnel diode has a nonlinear characteristic. So when you change the bias voltage a little bit, your oscillation waveform will change a little bit. That changes the frequency a little bit. So in other words, if this DC voltage is drifting around, your oscillator frequency is drifting around, and that kills your resolution. So that's why we use this voltage regulator here. So this is RF powering design, where I have 3 equations. With the first one is the voltage gain, second one is the efficiency, the third one is what we call beta, which is in the first 2 equations. So it can be shown that given the geometry I have shown and loading condition, there exists an optimum powering frequency where beta is equal to 1 to maximize the efficiency. And in our design, the L1 is about 3 microhenry, L2 is about 6 microhenry, and this R load, 2.56 kilo ohm, is actually the equivalent AC resistance looking into this rectifier diode. And with these, we calculate the optimum frequency to be around 1.7 megahertz and a voltage gain about 3.2. So to achieve that 1.2 volt DC after rectification, we need a input voltage of 880 millivolt peak to peak. And the external RF power is 44 microwatts with a received RF power of 800 microwatts. That gives us an efficiency of about 2%. So next we test this sensor under the fully wireless configuration where we have this RF power transmitting coil out here and RF power receiving coil in here. So it's pretty much the same as the DC power condition. And another important thing here is the powering frequency is only 1.7 megahertz, whereas the oscillator nominal frequency is 38 megahertz. So you can see there is a huge frequency separation between these 2 frequencies. This is very desirable to minimize the interference between these 2 RF signals. So what could happen when you have these 2 frequencies very close to each other is that your incoming RF power frequency or signal can injection lock your oscillator or injection pull your oscillator. And in that case, your oscillator frequency will not be determined by the glucose change. And in that case, your frequency will be primarily determined by the incoming frequency. That defeats the whole sensing purpose. So this is the RF-powered prototype wireless sensor module assembly. And in this picture, you can see this is the oscillator PCB with the RF receiving coil here and the sensing coil down here. So there is another transparent layer between the bottom of the PCB and the sensing coil, which is a convex shape PDMS layer. The reason I had that layer there is because I want to push this coil all the way down to the bottom of the package to minimize the gap size. And this is the top view of the package, and as you can see, it's still kind of big right now, but the reason it's big is because so this peripheral region where we have 6 holes is only for mounting purposes. And once we finalize our design, these holes will disappear and the overall size will be greatly minimized. And this is the bottom view of the package. As you can see, the sensing coil is right here. And this transparent layer is actually the 80 micron 3D printed layer. And now I adhere the glucose sensitive hydrogel sample onto this adjustable platform and make sure to align these 2 things and assemble these 2 parts using 3 screws and keep making adjustment until I see that frequency corresponding to the 50 micron depth size. And next, I will put everything in the testing container with the glucose, with the control glucose concentration, and the receiver antenna should be somewhere here, which is not shown in the picture. So now let's talk about frequency stability. So remember, we had a 5 kilohertz per day frequency drift tested under DC power condition. And here what I've done is I recorded the oscillator frequency tested in air and powered by RF powering, without glucose, without hydrogel, without metallic sensing plate, no nothing, just oscillator itself. And as you can see, the oscillator frequency drifts around. And I recorded the temperature simultaneously, and as you can see, they carry similar signature. So when there is a temperature increase, the frequency decreases, and the temperature decreases, the frequency increases. In other words, there is a negative coefficient in the oscillator frequency, even if there is nothing. So here we observed a frequency drift of 8.5 kilohertz per day under a room temperature variation about 1.6 degrees Celsius. And then we move everything into 1x PBS solution, and I did this frequency stability test again, because that's where we do our glucose characterization. And we observed similar signature here. So the temperature decreases, the frequency increases, and they kind of lines up. And these numbers are very close to that 5 kilohertz per day frequency drift I talked about earlier. So this is the result I got from a fully wireless design, where I use RF powering. And so here I changed the glucose concentration from 0 to 10, back to 5 to 0, and all the way back to 15. So of particular interest is this portion, is when I increase the concentration from 5 millimole to 10 millimole from here to here, I observed the frequency change about 18.96 kilohertz. And when I decrease the concentration from 10 back to 5, this frequency change is about 18.35. So they're very close, but I do observe a small amount of hysteresis. And a similar thing was observed in the lower concentration region. And comparing these two, you can see, once again, at lower concentration, the sensor is more sensitive, and at higher concentration, it kind of saturates. So with that, I'd like to draw my conclusions. A wireless hydrogel-based glucose sensor employing an inductive sensing technique has been demonstrated for future implantable applications. The sensor module under RF powering is capable of sensing and wirelessly transmitting the glucose information within human physiological range. The proposed packaging scheme demonstrates a reliable operation in the prototype testing environment. Sensor module can be further miniaturized to a few cubic millimeter size by employing integrated electronics. Reference oscillator and FSK modulation scheme will be considered to circumvent frequency dependence on ambient temperature, because this is what limits our sensing resolution. And minimizing hydrogel hysteresis and response time will be our future research focus. The authors would like to acknowledge the research support from US National Science Foundation. Thank you for your attention.